Section 6.1, Solving Linear Systems Using Matrices. We're going to learn in this section how to solve a system of equations, two equations using matrices. So in order for us to be able to do so, we first need to introduce what is a matrix. So what is a matrix? So we'll learn a little bit about matrices. And then in the next section, we're going to learn about operations with matrices. But here we just introduce them, what matrices are about, and how we use them to solve a system of linear equations. So by definition, we say a matrix is a rectangular array of numbers. Or symbols or expressions. So how do you write matrices? Say I have a matrix. We use a bracket for that. Some people use large parentheses. It doesn't matter. This has how many rows? This has one row, two rows. So that's two. How many columns? One, two columns. So we call it 2 by 2 matrix. And the 2 by 2, this is called dimensions. Dimensions of the matrix. Always row by column, not column by row. So we always think about it as 2 rows by 2 columns, 2 rows by 2 columns. The stuff inside this bracket, this stuff, these are called elements of the matrix, elements or members of the matrix. So A, B, C, D are the elements of the matrix. So if we look at this matrix 2, 3, 7, what are the dimensions of this? This is only one row by 3 columns. So I write as a subscript right on the right lower side, I write 1 by 3. Like doesn't mean 1 times 3, it's just 1 by 3. That's a symbol for that. So those are the dimensions or the size of the matrix. Again, always row by column, row by column. So if we need to look at another example, negative 8, 3, 1/2, 0, 5, square root of 2. This is 2 rows by, even if you want to add more, you can do so. This is 2 by 3, 2 rows by 3 columns. So if we are asked to determine the size of each matrix, number 1, 1, 4, 2, 5, 3, 6. So this matrix is how many rows? 2 rows. So 2 rows and 3 columns. So we say it's 2 by 3 matrix. This is the dimension. You don't have to write 6. It's not multiplying again. We just write 2 by 3. Another example, number 2, A, B, C, D. How many rows? 1, 2, 3, 4 rows by 1 column. 4 rows by 1 column. Now remember, we need to learn here is how to solve system of linear equations. So what does that mean? If you remember, we did this before. Let's say we are given a system of equations like so, and we need to write down or solve this system of equations. So two things good to know here, or good to get. We have what we call coefficient matrix. So the coefficient matrix is the matrix that involves only the coefficients of x and y. So 2, 1, 2, 1, you see it, and 1, negative 1. 2, 1, 1, negative 1. This is called So this matrix includes the coefficients of x and y. Now we have another matrix, it's called Augmented Matrix. This matrix includes all the coefficients, so the 2, 1, 1, negative 1, and then we put a vertical line. It could be a dotted line or it could be a dashed line, and then we put the constant that you see on the right side, 8, 1. So we put 8, 1. We're going to see why we're doing this. So let's practice a little bit more on this, right? The augmented matrix for each system of equations. Each system of equations. So 2x plus 7y equals 8. X equals, let's say, 11. And then we're going to look at another one. X equals y plus 11. And y equals 5 minus 3x. So this becomes 2, 1, 7. There's no y here, so that means it's 0y. So that's a 0. We don't leave it blank. We must put a 0. 8, 11. So everything is arranged in the way it's x's, y, and numbers. X, y, numbers. Look at this one. It's not arranged x, y equals numbers. So what do we have to do? On the first equation, we subtract y on both sides. So now it's x minus y equals 11. For the second equation, we add 3x to both sides. So 3x and keep the plus y the same equals 5. If there's no sign, means it's addition. So now it's written in, both equations are written in the form x, y equals number. So it's 1, negative 1, 3, 1, and then 11, 5. That's the augmented matrix for such a system. Can the system be a 3 system, like 3 equations in 3 unknowns? Yes, we can have 3. Let's say they give us x plus 2y plus 3z equals 5. 2y minus x plus z equals 0. Y plus z minus x equals 8. So here we need to be careful about the order. It should be x, y, z equals numbers. So if you want to go straight forward and write the augmented matrix, we need to look at the x's. The coefficient here is 1. In the second equation is negative 1. In the third equation, negative 1. The y's. Coefficient of y is plus 2, and plus 1. So there's a 1 here. So 2, 2, 1. For the z's, we have 3, 1, and another 1. And the other numbers, they stay as they are. They are already on the right side of the equal sign. Now, what about if we go backwards? Can we go backwards with this? Let's say they ask us to write the system of equations. System of equations represented by each augmented matrix. So let's say the first one, 2, 4, negative 3, 7, 0, 1. So they give us the augmented matrix, and we need to write down the system of equations. So write down the system of equations. So it's, say the variables are x and y. 2x minus 3y equals 0. From the second row, we get 4x plus 7y equals 1. We're going to look at another example. 1, negative 2, 4. 4, 3, 0. 2, 3, 4. 3, 0, negative 11. So now we have 1x plus 4y plus 2z equals 3. I assumed x, y, z are the variables. You can put a, b, c, it's fine, any three variables. Negative 2x plus 3y plus 3z equals 0. Then 4x plus no y plus 4z equals negative 11. Now if you put 0y in the third equation, that's fine too. That's totally fine. One other example. Let's say we have 1, 0, 0, 1 and then 2, 3. 2, 3. How's that going to work? Well, again, 1x plus no y equals 2. No x plus y equals 3. So this shows you like x equals 2 and y equals 3. Now since I wrote that 1, 0, 0, 1, we can write a note here about this matrix. It's a special matrix, 1, 0, 0, 1. This matrix is called the identity matrix. It's a 2 by 2 identity matrix. It can be, if you just put 1 like this by itself, that's a 1 by 1 matrix. It's also identity matrix. We can have 3 by 3 identity matrix. The identity matrices, they have, this is called their main diagonal, the highlighted one. The entries or the members on the main diagonal, they must be 1 and everywhere else zeros. Everywhere else zeros. So the entries or elements on the main diagonal of the matrix are 1s, and the remaining entries are zeros. So again, as I said, this is 1 by 1. So this is 1 by 1 identity matrix. We have the 2 by 2 identity matrix. This is 2 by 2. And then there's 3 by 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. That's 3 by 3 identity matrix. So remember, the main title of this section is to solve linear system of linear equations using matrices, but we haven't done so. We have been just introducing things here and there. So what we do, why do we need matrices here? Because in matrices we can perform operations on their rows. Those operations are called row operations. For example, let's take a matrix 2, 3, 1, 4, 5, 0, and I want to perform some operations. Let's say the operation I'm going to do, R1, arrow, R2. Some people write it like this, R1, R2, and they put like a curve on the top. So what this is saying, this says switch row 1 and row 2, or interchange row 1 and row 2. So this means interchange row 1 and row 2. That's what this means. So how do I interchange them? This means row 1 becomes row 2 and row 2 becomes row 1. Like that. Let's say they give us another example. Let's say they give us negative 3, 0, 6, 9, 12, 3 here. And we are asked to perform, let me write it down here, perform negative 1/3 R1 and R1. So what does that mean? This is saying multiply row 1 by negative 1/3. Okay, multiply row 1 by negative 1/3 and add the result to row 1. So this means 2. So multiply row 1 by negative 1/3, and whatever you get, you add it back to row 1. So what would that give us? So if I multiply row 1, the negative 3, the first entry, this one, by negative 1/3, that's going to give me positive 1. Now if I take that 1 and add it to negative 3, to this negative 3, because it says add it to negative 3, that makes it negative 2. If I take that second one in the first row, 6 times 1/3, that would give us 2. 2 plus 6 is 8. Then take the next entry, 12. 12 times 1/3, that's a 4. Add 4 to 12, that's 16. Then the second row stays the same. Second row stays the same. Next one. Let's say we have 2, 4, 3, 1, 8, 3. And we are asked to perform negative 2R1, 2R2 plus R1, and add the result to R1. Notice in the previous example, we did not change anything, modify row 2, so I copied it down as is. We must copy it down, we cannot just leave it alone. Here, what we're gonna do is, we are going to multiply row 2 by negative 2. Okay? And whatever result we get, we add it to row 1. Okay, we add it to row 1. So let's see what that means, and then that result goes to row 1. So if you take this, that's row 2. That's row 2. Multiply 4 by negative 2. 4 times negative 2 is negative 8. Add it to row 1. So negative 8 plus 2 is negative 6. Multiply this by negative 2. You got negative 2. Add it to the top one, becomes 1. Multiply this by negative 2. That's negative 6. Add it to 8. That's a 2. And then row 2 stays the same. We don't change row 2. We do not modify row 2. No changes. Let's look at another example. 3, negative 2, 8, 1, negative 7, 4. We are asked to perform part 1, 2 row 2 plus row 1, and the result will be in row 1. Result will be in row 1. So multiply row 2. This is row 2. Multiply each one of them by 2. So that gives me negative 4 for the first one. And add it to this one. That gives me negative 1. Multiply the second row by 2. So the 1 by 2 is 2. Added to 8 is 10. 2 by 4 is 8. Added to 7 is 1. Keep the second row the same. Another part. Negative 3 row 1 added to row 2. So the result will be in row 2. Same problem. So I'm going to multiply the first row now by negative 3. So 3 here by negative 3 is negative 9. Added to negative 2, that's negative 11. What happened to row 1? There's no change on row 1, so we can simply write it down. 3, 8, and negative 7. That will help me also on this side. So multiply This by negative 3, that's negative 24. Negative 24 added to 1, it's negative 23. Okay, next one, multiply the negative 7 by negative 3, that's 21. 21 added to 4 is 25. Okay, so these are just quick operations. We call specifically row operations on matrices. So now what we're going to do is we are going to see how do we put all this together to be able to solve system of equations. And this process is called Gaussian's elimination. Gaussian elimination. Goes back to the mathematician Gauss. So Gaussian elimination is to be used to solve system of equations. System of equations. So what is going to happen? You're going to be given a system like this, system of equations. We're going to use the augmented matrix we learned earlier and write it as augmented matrix. Okay, write this or find the augmented matrix of this. It's going to be something. Some number equals some number, and some number. After we got the augmented matrix, we need to write it with using, let's say, using row operations. With row operations, you write it in this form: 1001, and then some numbers here, AB, let's say, AB. So basically, you want to get this matrix to be the identity matrix using row operations. Okay, and then whatever we get on the right side, as you can see, we have A and B. So what do we do with the A and B here? And so how does that solve the problem? Well, because when you write it in this form, then this means this one means 1x. So then 1x or x will equal to A. And this one here down is 1y, so y equals b. Remember, the main goal is to solve for A and B. I mean x and y. And that's how this helps us. So we will get whatever numbers we get for A and B, those will be for x and y. Let's try to solve this system of equations. 2x minus y equals 7. X plus 3y equals 14. Okay, so let's try to solve this. Yes, you can solve this with elimination. You can use substitution. You can use graphing. But we're going to solve it using matrices. So first, as I said, we write the augmented matrix of this. 7, 14. And watch the process how we do this. Okay, this is very important process. And what I'm going to say now, it's very, very important. What we do here, we clean it column by column. Column by column. What does that mean? Means if I go back up to this, the first thing I want to get is this number to be 1. And then I'm going to use that 1 to make this 0. This means I cleaned the first column. Means I made the first column 1, 0. The next one, we get this to be 1. From that one, I try to get this to be 0. Then I clean the 2 columns. So this is very important what I just said. Clean column by column. So make sure the first number on the upper left corner, always 1. Is it 1? No, it's 2. But notice in the second row, there's a 1 here. So what I can do, as a first step, I can swap row 1 and row 2, like interchange them. So make row 1 row 2 and row 2 row 1. Okay, 2, negative 1, 7. So that's the first thing. Okay, now I have this number up there. This number is 1. This number in mathematics we call the pivot number. So that number is 1. I'm going to use that number here. I'm going to use that number to clean up the first column. So I already got 1 up there, as you can see. We have 1. Now I want to make that number 2 down there. I want to make it 0 right below the 1. How do I make that 0? I'm going to take row 1 multiplied by negative 2 and add it to row 2. So add that to row. If you like to write it the way I wrote it earlier, add it to row 2, and the result is going to sit in row 2, right? Add it to row 2. So let's see, if you multiply the first number, which is 1, by negative 2, that gives us negative 2. Add it to row 2 is 0. Multiply 3 by negative 2, that's negative 6. Add it to 1 is negative 7. Multiply the first one by negative 2, that's negative 28. Added to 7 is negative 21. What happened to row 1? Well, it stays the same. So now watch, I clean the first column. Clean the first column means I got the first column to be 1, 0. Now, I'm going to make this number 1. Notice how this number and this are multiple of 7. So what we can do is multiply row 2 by negative 1, 7. Okay, and then put the result in row 2. So what we get, row 1 stays the same. I'm not performing any work on that. This 0 and the other one is 1, and the next one is 3. I got 1, 3. See, I got 1 down here. Now I'm going to use this one to make the 3, 0. So how do I make the 3, 0? I need to multiply the second row by negative 3 and add it to row 1. So the result is going to go in row 1. Okay, so row 2 stays the same. Now negative 3 times 0 times that 0 is 0. Added to 1 is 1. See, it did not affect the 1. And that's what I want. I want to keep it 1, 0, like so. Now multiply this one down in the middle by negative 3. And that's negative 3. Added to the 3 above it, that makes it 0. Now negative 3 by this 3 is negative 9. Added to 14, which is the one right above it, makes it 5. Now look, this is the identity matrix. I use I for identity. It's a 2 by 2 identity matrix. So now this means this is 1, 1x. So x is 5. And from the second row, y is 3. X is 5, y is 3. Let's look at another example. Let's say we are asked to solve, this system, x minus y equals 2. And 3x minus y equals 12. Well, the first thing, I make sure it's written in xy equals number, which it is. So the augmented matrix for this is 1, 3, negative 1, negative 1, and 2, 12. You can read it horizontally or vertically. It doesn't matter how you read it. Luckily enough, this number here is 1. So I'm going to take that number 1, multiplied by negative 3, and add it to row 2. So the result will be in row 2. 1, negative 1, 2. Multiply the first one by negative 3. So negative 3 by 1, negative 3. Add it to the 3 right below, that's a 0. Negative 3 by 1 is 3. Added to negative 1 is 2. Negative 3 by 2 is negative 6. Added to 12 is 6. So I cleaned the first column so far. Now I want to get that 2 in the second row to be 1. This 2, I want it to be 1. As you can see, 2 and 6 are multiples of 2. So the easiest way is to multiply row 2 by 1/2. And then the result will go in row 2. So that's a 1, 0, negative 1, 1, 2, and that's a 3. So row 1 stayed the same, but row 2 becomes half of the previous one. So now I got a 1 down here. So we have a 1. I'm going to take that 1, multiply row 2 by nothing, basically. Just add row 2 to row 1. And the result will go in row 1. So row 2 stays the same. Row 1, 0 plus 1 is 1. 1 minus 1, 0. 3 plus 2, 5. Again, from here, x is 5 and y is 3. So now, when we lecture these topics in person, students say, wait, why do we have to go through this long process? If I can just simply multiply the first equation by negative and use elimination, I just add them. And it's really a simple process comparing to this process. So that process might take maybe 20 seconds, 30 seconds to solve the system. But this one is taking minutes to be able to finish it, assuming you know how to perform row operations on matrices. Well, the idea behind this is that because we're applying to 2 by 2 matrix, you don't see how effective this is. But in fact, when we go to 4 by 4 or 5 or 6 equations and 6 unknowns, then the matrices will be way more helpful than using elimination or substitution, because you're going to get lost with the equations. But when we use matrices for a large number of system of equations, then it keeps all the work more clean. In that sense, you clean column by column and go through all the row operations to get the left side of the matrix to be the identity matrix, and then from there you will be able to solve for the variables.